Day 16 of 90. Today we are building file system tools for security work. If you are doing integrity monitoring, forensic evidence collection, or malware scanning, everything starts with traversing directories and examining files. I will show you 4 patterns that handle the core operations you will use in every security automation project. First up, recursive directory traversal with os.walk. This generator yields a tuple of directory path, subdirectory names, and file names for each level of the tree. For security scanning, you want 3 additions on top of the basic loop. First, filter by file extension so you only examine relevant files like executables, scripts, or config files. Second, set a maximum file size so your scanner does not choke on huge disk images or database dumps. Third, wrap every stat call in a try-except block because permission-denied errors will crash your scan otherwise. One important trick: modify the dirnames list in place using slice assignment. This tells os.walk to skip directories you do not care about, like hidden folders or vendor directories. Without this, your scan wastes time descending into irrelevant subtrees like node_modules or .git. Next pattern, path traversal prevention with pathlib. Any security tool that accepts user-supplied file paths must guard against directory escape attacks. If someone passes //etc/shadow as a file name, they can read files outside the intended directory. The defense is straightforward. Use pathlib resolve method to convert the path to its canonical absolute form, then check that the resolved path still starts with your allowed base directory. If the resolved path escapes the base, reject it immediately. This is a 3-line check that prevents an entire class of vulnerability. Every web application, every API endpoint, and every CLI tool that processes file paths from untrusted input needs this validation step. Now for file integrity monitoring. This is one of the most practical security tools you can build in pure Python. The concept is simple but powerful. Phase 1. Scan a directory and compute SHA-256 hashes for every file you find. Store those hashes in a JSON file as your known good baseline. Phase 2. Rescan the same directory later and compare the current hashes against the stored baseline. Any hash mismatch means a file was modified since the baseline was created. Files present in the current scan but not in the baseline are newly created. Files in the baseline but missing from the current scan were deleted. Together, these 3 checks catch unauthorized modifications, planted backdoors, and evidence tampering. One critical implementation detail: always hash files using chunked reads. Read 8 kilobytes at a time and feed each chunk to the hash object incrementally. If you read a 2 GB forensic disk image into memory all at once, your script will crash or your system will start swapping heavily. Chunked reads keep memory usage constant regardless of file size. Forensic metadata extraction goes beyond just hashing. During incident response, you need the full picture for every file: size in bytes, ownership as UID and GID, permission bits in human-readable format, and all 3 file system timestamps. The creation time, modification time, and last access time all help reconstruct what an attacker did and when they did it. Python os.stat gives you all of this raw data. Convert the timestamps to UTC-ISO format for consistent logging across different time zones. Capture the user and group IDs to identify which account created or modified suspicious files. Use the stat module file mode function to convert the raw mode bits into a readable string like RWXRXRX. Combine all of this into a structured JSON evidence log that your incident response team can process and correlate with other data sources. The combined scanner ties all 4 patterns together into a single tool. Walk the target directory with os.walk, check each file hash against the stored baseline, flag anything that was modified within the last n hours, and log full forensic metadata for every suspicious finding. You end up with one script that answers the 3 questions every security analyst asks during an investigation: what changed, what is new, and what looks suspicious. In production, you would pipe these findings to a SIEM or alerting system. That wraps up day 16. Tomorrow I will add automated alerting and log correlation on top of these file system operations. See you on day 17.